Okay. Hello. This is Gil-Ho again. Thank you very much, and I would like to take this privilege, a chance to introduce our recent work on nano devices. So especially, I want to focus on this under bound states formed inside of the graphene-Josephson junction. So this is one branch of my research direction, focusing on the fundamental physics. And although I'm not present today, there is another branch forwarding to this application, which use the graphene-Josephson junction as a very sensitive sensor, and for the photons and phonons and hopefully dark matters as well. But today I want to focus on this this physics. So this is basically my group member. Actually, this is one of the old photos, so that it includes my PhD advisor here, who retired a few years ago. So we are basically experimental physicists working on nano devices based on some quantum materials and usual superconductors. We're not measuring at the very low temperature, looking for the quantum behaviors of these devices using Diffraction at the millikelvin range. So we are especially interested in the superconducting devices because the superconductors are basically macroscopic quantum objects, so that experimentally it's easy to handle because it's macroscopic, but also it shows very interesting quantum behaviors. These are some of the examples of quantum devices that we are working on: the graphene-Josephson junction and topological materials-based Josephson junction and high-TC material-based devices and graphene devices. I prepared two topics. One is that generation of steady Floquet state, which is one of the prominent example of non-equilibrium quantum system. In the condensed matter physics, we are very interested in, so our kind of map for this material is band structure. So they are changing the structure of this material, or recently we are kind of making some artificial material by twisting angle of van der Waals material to make this flat band, magic angle graphene, or we pressurize the material to change the property, or we shine the light, transiently make some, for example, room temperature conductivity. Yeah, possibly. So this kind of engineering band structure is kind of one of the paradigm in the condensed matter physics. And today I want to focus in this light matter combination. So in condensed matter lecture, we learn about this Bloch state. So in the bare electron in the vacuum, we have this quadratic band structure in the energy momentum relationship. But in the metal, we have, or material, we have this periodic potential, which give us a periodic, spatially periodic potential that make this dispersion copied along the k direction. So we call this a quasi-momentum. And in the cross-section area, we have gap opening so that it makes a band gap. So we call this a band structure, and we call this a Bloch state. So there is a counterpart when you are doing this time-dependent potential, so that the energy is not conserved, so it's not in equilibrium. But for example, we shine the light, it's basically time-periodic potential, so that electron feels this potential, then it copies the dispersion relationship along the energy direction, so that we call this quasi-energy from now on, and this is Floquet state. So in general, people call it Floquet-Bloch state in general. So this is one of the example. If you know, the Kapitsa pendulum is kind of classical, one of example of this non-equilibrium physics. So when you shake this pendulum up and down very much, then the pendulum usually swing at the lower bottom, but when you're shaking very much, then the pendulum prefer to stand up actually, so that their local the global minimum potential actually changes by shaking the system, basically time-periodic potential environment. So there is, of course, a quantum version of this, and people have been working on this Floquet engineering. Usually, early days, people are using this atomic system because shining you need some quantum object and interaction with the light. So people have been working these kind of things, and even they make this topological system out of this blockade state by using this time period potential. And there are also interesting proposals to make this topological blockade state out of non-topological materials. But in condensed matter, it's not so much studied as far as I know. But one of few examples is that this AAPPS experiment done by Professor Nuganik's group at MIT. They basically measure the surface state of topological, 3D topological material, and they put this IR light pulse on the surface so that they can see this transient blockade state. You can see that the original band structure is copied up and down, but they diminishes back to the original state because this light is pulsed. So when the light ends, the blockade state come back to the original state. So the reason why they have to use this pulse laser is that they need very, very strong light, strong light to see this blockade. But let me consider the blockade interaction is okay, sorry. So because they are using so strong lights, they are suffering this heating problem. So that they because this is time period potential, they shake the electron continuously. Then it will eventually heat up the electron temperature and goes to the infinity. If that the system is closed system. So that is one of the major problems to study this blockade state in physics. So our approach is basically using microwave light rather than the optical light. When the frequency is reduced, then the electric field strength you need to see the blockade state is reduced like square, omega square. So for example, if we use 10 gigahertz, then the frequency is now 10,000 times smaller, then the electric field you need is 10 to the 6 times smaller, so that heating is also very, very weaker, so that we can may be able to make this blockade state steady, so that we can study more details of this interesting non-equilibrium quantum physics. So I will introduce my experimental platform. So my platform is Josephson junction, which is basically two superconductors coupled through this non-superconducting material. When the superconducting order parameter overlap each other, they make Josephson coupling, so that even the inserted metal is non-superconductor, it can accommodate the supercurrent called Josephson current. This is kind of megascopic picture, but in microscopic picture, what is happening is that this one electron going to, in the normal metal, going into the superconductor, but there's no quasi-particle state inside of the superconductor, so that the only option it can take is to grab another electron, which has different energy, form a Cooper pair at the zero energy, and get into the superconductor. But this electron just grab another electron so that it reflects the whole state back to the left. Then this whole state do kind of under process again and reflect it as an electron. So it goes back to the original point, position. So when the electron phase accumulation for this one cycle equals to 2 pi times integer number, then it can form some kind of bound state. It's basically the particle in the box problem we learned in quantum 101, right? In the particle in the box. So this forms so-called under bound state inside of the Josephson junction, and for this one circle of this electron, the one Cooper pair transferred from left to the right, which is the Josephson current that I just described before. And this bound state has this kind of phase-dependent spectrum. So you know the energy is bounded by superconducting gap, and it's as a function of phase difference between these two superconductors. So we can take this as a kind of artificial band structure of 1D material. Although this is not a real material, but basically energy disperses as a function of phase difference. Now the phase difference phi acts as a quasi-momentum in the real condensed matter system. Yeah, that's basically our system. And experimentally, to see the underbound state, we need some kind of tunneling spectroscopy, like STM people do. They use this tunneling spectroscopy TF on surface of some unknown material and measure the energy-dependent differential conductance, so that gives us the energy-dependent density of state. So because this graphene is 2D material, and our idea to make this tunneling proof is to put some superconducting material on the side of the graphene and make a tunneling contact to the graphene, so that this aluminum side tunneling contact acts as a proof that can prove the density of state of the underbound state formed inside of the graphene. So the device looks like this. So basically this is the schematic. So this is the graphene, and we make a superconducting contact on these two sides, but we make it into a ring so that we can control the phase difference between these two superconductors by applying magnetic field and form the underbound state inside the graphene, and use the tunneling superconducting contact to the side of the graphene and measure the differential conductance as a function of voltage. That is oscillatory, shows oscillatory behavior as an magnetic field. Basically, that shows this oscillation that I showed in the underbound state. So this is one very cute idea to use tunneling contact, but it's powerful. So this is our starting point, and basically we shine the microwave and see what happened. So experimentally, we use this low temperature measurement system. We make RF signal at the room temperature and plug it into the cryostat and shine on the device, and make the electron inside of the graphene interact with the microwave photons. When we are doing that, so basically this is the underbound state without microwave. The original underbound state shows a pair electron-hole symmetric energy band. When the microwave power increases and more, it makes this Floquet state of the distance of energy distance equals to HF. F is the frequency of the microwave. So, for example, for this example, when the power is low, we only have two pair lower and upper state. That is lower and upper branch of the underbound state. And when the power is increasing, this original state diminishes while this underapp state, Floquet state peaks emerges, and it shows basically oscillatory behavior as a function of power. And I want to emphasize that this measurement was not done by pulse microwave and transient measurement. We actually shine microwave continuously and keep potential there, so that the Floquet state actually forms steady, so that we can measure it very slowly, and so that we can see the details of the underbound state. So here I recap the reason why we use much lower frequency gain, because the Floquet interaction parameter beta is proportional to the electric field divided by the frequency square. So when we decrease the frequency of the light from terahertz to gigahertz, the electric field that we need is lowered by a factor of 10 to the 7th. Then, because the heating is the electric field squared, the heating is 10 to the 14th times smaller, so that even this small power is well dissipated by electron-phonon coupling inside of this graphene, so that we were able to generate this steady Floquet state. So I think this is one interesting way to study this non-equilibrium quantum physics, Floquet states, in the steady manner. So we are now thinking, these are the details of the theoretical fitting that basically predict all the quantitative behavior of the measurement that we've done. Also the theory well described the power dependence and the spectrum well, and the frequency dependent behaviors, the energy gap between original state and the Floquet state is well described by HF as expected. So this is kind of one example of making this Floquet state in the graphene-Josephson junction. We can even make some more circular polarized microwave light to make some topological flow cascade, or we can replace the graphene with some topological material to study this Majorana zero mode interaction with the microwave, so that there is actually one theory. I don't know whether it's possibly done experimentally, but at least there is a suggestion to braid non-abelian anion, the Majorana zero mode, not in the real space, but in the energy-time domain. So that is another interesting direction we can think about. Okay? So yeah, this is the first part. And I want to extend this underbound state study into multi-terminal Josephson junction now. Now, as I told you, this two-terminal Josephson junction gives this kind of one-dimensional band structure. If you think the x-axis has a quasi-momentum. But we can extend this idea to multi-terminal Josephson junction. For example, n-terminal Josephson junction, there is n-1 independent variable, phi 1, phi 2 to phi n-1. So then it will represent n-1 dimensional band structure, sort of. Which, for example, in a real world, we are living in three-dimensional world, I believe. Then the band structure up to the most three-dimensional band structure is like the most experimentally accessible. But using this abstract band structure as an underbound state, maybe we can think about even higher dimensional band structure and study more interesting physics. And there's also interesting idea above four-dimensional four-terminal gate cases, people can suggested to make a topological band structure out of underbound state, for example, Y point over here, or three-terminal with floquet driving. You can, basically this Hamiltonian looks exactly like Haldane Hamiltonian, so that we should be able to study this topological material, similar physics. Okay. Just answer. Okay. Great. Yeah, so because we studied two-terminal, now we move on to three-terminal. So this is the device geometry. The graphene at the center, and there are three-terminal Josephson junction, and the two phase differences, phi L and phi R, can be independently controlled by the flux line that we fabricated on the same substrate, like the flux tube. So by tuning this current flowing each flux line, we can tune this phi n and phi r independently and measure the density of state of the underbound state formed inside the graphene using superconducting tunnel contact. Then we can get this sort of two-dimensional band structure that is, it looks, if you are familiar with, this looks like AAPPS data taken by the graphene, but it's not really momentum, it's phase difference, phi n and phi r energy, and it shows this cone shape of band structure. So I want to explain why it looks like that. So in the theory model, the simplest, to explain the core physics, I will just use a simple model to get some physics. So basically the underbound state will be dependent on the scattering matrix of the graphene. How they are connected will be encoded by this scattering matrix, which should obey a certain symmetry like time recursive symmetry. And one example is there, and this is our simplest model you can think about. The gamma basically parameterized how reflective this superconducting contact is, but this is just one of the possible model. This is not the only model. But basically, with this simple model, we can calculate the underbound state, and it looks like that. And it shows this nodal line band structure, topological band structure. And this is similar to the actual nodal line semi-metal in the real material. And okay, so that's why near the zero energy, we expect a linear band structure as a energy versus phase difference. And that's what we are seeing over here, here, the linear band structure. And if we are doing energy cut over there, we actually, in the simplest model, we expect this nodal line, the line So only the line should be red. But this square is, this triangular is all red. And that is because the model was too simple to explain our experimental situation. The graphene scattering matrix is not, there are so many conducting mode inside of the graphene. If you calculate the Fermi wavelengths of 50 nanometer, and the graphene size is like a micrometer, so there should be about like hundreds of conducting mode. So there should be 100 of underbound states all merged together and measured in the experiment. So that's why. So in the real situation, so there's depending on the gamma value, you have different size of the ring. So because your system has all different possible scattering matrices, all this ring merged together makes a plane colored. Okay. Anyway, so this is a bit details, but okay. I wanted to show the energy-dependent cut at different energy, but basically I want to say that this random matrix theory can well explain the experimental data we've measured. So this basically demonstrates this multi-terminal Josephson junction can serve some higher dimensional band structure like underbound state. That this is kind of starting point. So this is starting point of studying the steady flow test state in the device level, and this is the starting point of studying higher dimensional band structure and possibly topological band structure. In the combination, there is also a possible combination of doing flow test state out of multi-terminal Josephson junction as well. Okay, so yeah, so basically this is the story I prepared today, and thank you very much.
Of course, we have some time. Can you take some question or comment for each talk? Okay. Please.
At the very end, you shortly mentioned this random matrix theory. So your system is not random system. What? How does it connect it?
The thing is, so because the graphene size is like 1 micron size, and the wavelength of the electron, the Fermi wavelength is order of 50 or 20 nanometer. So if you divide 1 micro by 20 nanometer, there is 50 state, but there is a 4 degree of freedom, so 200. So there are like hundreds of conducting channels inside of the graphene. So you have to think about few hundred different scattering matrices. Each makes different underbound state, and what we are measuring is basically a sum of that. And we think that because there are so many different conducting channels, which has all different superconducting contact transparency gamma. So it effectively well described by the random matrix theory. So we virtually scan all possible parameter space because we have too many conducting channels. So to give more neat result, we better to move to a smaller size of the graphene so that we deal only a few conducting channels, hopefully 1 channel, and maybe we can use it as an unwrapped level qubit as well. That is one direction we can think about. Thank you.
Okay, thank you very much. And
thank you very much.